Hello chemistry students. On our last video we talked about the theory behind carbon-14 dating, and today what I'd like to get into is how do you actually solve those problems. So here's a problem that some researchers had. They found a pair of beautifully preserved extinct cave lion cubs from Siberia, and they wanted to know, well, how old are these things? And so they had to do some carbon-14 dating on this thing, and they took the samples and figured out that these things are 12,000 years old. There's some people who would love to clone these things and bring them back into the environment. These disappeared at some point, obviously, and these ones were alive back during the last ice age. All right, let's get into how they kind of basically solve some of these questions and what we're going to be doing today. So our two objectives today, the first thing we're going to be doing is we're going to be doing a quick review practice of reading a half-life graph, particularly a carbon-14 one. And then what we're going to do is we're going to get into how to use a basic data table to solve just a basic carbon-14 problem. All right, so here's your first review. This is a bone containing 4 remaining grams of carbon-14 out of the expected 10 that it would have started with, presumably. How old would that bone be? If you answered 8,000 years old, you got it correct. If you didn't quite get that, you would be right over here. You'd say, oh, it has 4 grams remaining, and we're going to pull that over to our standard curve here. And when it hits that curve, we drop down. We get about 8,000 years old. If you got 7 or 9,000, that's okay. That's within the uncertainty, and I would accept those answers. Let's move on. So carbon-14 data table is going to look very similar to the one that you set up for all the other half-life problems. Where you're going to notice a difference, though, is in our decay rate. That is a new column for us. Remember from our theory video, we said that the living decay rate of all organisms today is 15.3 decays per minute per gram. And so we're going to assume that that is the case. We're going to assume that that was the case in the past, that the sun has not changed and our air has not changed significantly. And so the new piece of data here that we'll always be using on these problems is the half-life will now always be 5,700 years. All right, let's fill out this data table that you would be using for most carbon-14 problems. So if we move to a first half-life, that would mean the material has to have only half of its original materials left. And as the definition implies here, we would have an age then of 5,700 years in order for half of that sample to decay. The decay rate then, as you would expect, would be down to about half of what it originally was. So once a sample is 5,700 years old, we would see a decay rate of 7.65 decays per minute per gram in our sample. If we continue our data table and move on to an additional 5,700 years, we've gone through an additional half-life, now we're up to 2, we now have a quarter of our sample left, half of this. This value will also have again. Okay, a third half-life will now bring us to 1/8, half of that. This is now where some students make a common mistake. Do not double this value. This is always adding 5,700 years, not doubling it. So please make sure you get that correct. This is 17,100 years. Your decay rate, though, will continue to have. If we go to 4 half-lives, we now again add 5,700 years, and we have our fraction and our decay rate. 5 would give us this, and 6 would give us this. If you need to, you can pause the video here to fill out your data table, and you will be pretty much using the same data table for all of our different problems. Let's move on. So this would be a typical carbon-14 problem. Here we have some gentlemen in the background who were doing research. They wanted to clone a mammoth, and they are still hard at work on that. And so what they did was they enlisted the locals in a particular area of Siberia that is known to have some of these frozen carcasses show up. And they said, hey, if you can find any of these remains frozen, please don't dig them up. Leave them there. Contact us. We can get you some cash for that. And this gentleman in the center here did find those tusks, and it was attached to a beautifully preserved mammoth. And that is what their job was. First off was find out, well, how old was this mammoth? And so this is the decay rate approximately that they were seeing in the carbon-14 samples that they had. So let's go ahead and figure out how old is this mammoth tusk pair. Okay, so what we're going to do here is we're going to set up our data table as I showed you. This mass left column, oops, should not be in there. Please ignore that. And what we're going to do is we are going to take our data table and we're going to continue moving down until we get to a decay rate of 1.91 decays per minute per gram. So once we have that, we can now cross-reference to our age and we can find out, oh yes, this organism was 17,100 years old when it died. So this is indeed our answer. Okay, this is the mammoth with the tusks. They still inside of it. They had carved this mammoth. The mammoth is inside of this block of frozen ground, and they didn't want to damage it at all, so they left it all intact inside there. If you notice, there's a very old Soviet helicopter outside there that was the only one that they could get a hold of that was heavy enough to actually, in terms of lift power, to pull something like this up and out, and they did get it out, and they have since thawed that mammoth out. This is an example of another mammoth. This was 39,000 years old that had been found. This one was a similar age. This is Buttercup, who my little stuffed animal is named after, and Buttercup was a baby. Here we have an additional mammoth that has been found, and this will give us an additional problem here. So here we know the approximate age of this Yukagir mammoth, and what we want to know is what would the carbon-14 decay rate be if we checked that thing out. So we're going to build a data table again, and this time we're after the age. So we're going to work our way down in our age on our column until we get to 22,800 years old. So here again, don't forget you're adding 5,700 years each time to the age column. And when we get to that column, we find out, oh, the decay rate should be about 0.96 decays per minute per gram. And so this becomes our answer. And we have now completed a couple different problems. So we have reviewed the reading of a half-life graph for a carbon-14 problem, and we have now used data tables to solve some simple carbon-14 data problems. If you would like to look at some more example problems, I will be posting an additional video showing you some additional interesting samples of things from the past that have been looked at for dating. And I will also be posting an advanced problem that some of you may want to look at in order to solve your most advanced kind of dating problems that I will give you. This has been Overlord. Over and out.